Now let's talk about electrical conduction in semiconductors. Charge carriers in semiconductors can be positive or negative or both. When an electron moves from the valence band to the conduction band, it leaves behind a hole in the valence band. Since semiconductors are charge neutral, when an electron moves to the conduction band, it must leave behind a positive charge, which is a hole. Right, this hole acts as a positive charge and participates in the carrying of a current. When an electrical potential is applied across an intrinsic conductor, the conduction of electrons and holes move through the material and hence carries a current. If you look at this diagram, where the applied electric field is from left to right, we can assume that this is between two plates where the left plate is positive and the right plate is negative. Because of this, the electrons want to move towards the positive charge, and the holes which are positive will want to move towards the negatively charged plate. Electrons moving towards the left and positive charges moving to the right constitutes a current moving towards the right. A pure semiconductor contains equal number of conduction electrons and holes. This is called an intrinsic semiconductor. A semiconductor that's been doped with a small amount of group 3 or group 5 atoms is called an extrinsic semiconductor. Now, let's look at some examples. The energy gap for silicon is at 300 Kelvin, is at 1.1. Sorry for that. The energy gap for silicon at 300 Kelvin is 1.14 electron volts. Find the lowest frequency photons that promote electron from the valence band to the conduction band. We see very clearly that E equals HF, and converting electron volts to joules, we have 6.63 times 10 to the power of minus 34 F equals to this amount of energies in terms of joules. Hence, calculating, we find that the lowest frequency is 2.7 times 10 to the power of 40, which is a light of 1090 nanometers, which is in the range of infrared light. In example 3, using band theory, explain why metals are opaque and why semiconductors are opaque to visible light but transparent to infrared light. First, metals are opaque because visible light have energies in the range of 1 to 3 eV, and this range it can be absorbed by the photons in the valence band to move in the conduction band. Since the light is absorbed, the metal is opaque to visible light. Of course, here we define opacity, that light is not transmitted through the object. So here, it is not correct to say that the light is absorbed forever. In fact, most of the time, the atoms falls back to their ground state or falls back to the valence band. After absorbing the energy, it moves to the conduction band, but quickly falls back to the valence band and reflects and emits a photon, and that is called reflection. Let's look at part B now. Semiconductors are opaque because the band gap is around 1 eV, and since visible light have energies around 1 eV to 3 eV, these photons are easily absorbed by electrons, and since the light is absorbed, the semiconductors are opaque to visible light. Also, they are transparent to infrared light because infrared light have energies of less than 1 eV. Hence, they cannot be absorbed by semiconductors. In fact, if you do your calculation, not all of the infrared light are transparent. Only a certain range of infrared light that is very long or longer than a certain wavelength are not absorbed. Hence, they are transparent to some of the infrared light. Lastly, in work example 4, by referring to the band theory of conduction, explain why electrical resistance of an intrinsic semiconductor decreases with temperature. Remember that in current electricity, I told you that semiconductor materials, when you heat it up, the resistance decreases, right? It is just like a polar bear. I told you that there are two main things you have to consider for electrical conductivity. One, which is the vibration of the atoms, and two, the number of charge carriers. I told you that for semiconductors, there is an increase of charge carriers, but I've never told you why. In this chapter, I've explained to you why there's an increase of charge carriers. So here, the answer once again, in an intrinsic semiconductor, the band gap between the valence and conduction bands is around 1 eV. Since the thermal excitations in the semiconductor are given to be around 0.04 eV, a small fraction of these electrons will gain sufficient energy to reach the conduction band. As the temperature rises, the fraction of electrons that are excited to the conduction band increases. This small fraction of excited electrons in the conduction band increases the conductivity of the semiconductor significantly and hence reduces the resistance.